Okay, today I'm going over a classic AP physics problem or a physics 1 problem from college or something like that, all right? Now it says this: consider the picture above. When released, the masses accelerate. There is friction between mass big M and the tabletop. Derive an equation for the coefficient of kinetic friction in terms of little m and big M, the two masses, and the acceleration of the blocks A. So I want to get a formula for mu sub k, the coefficient of friction. And in my formula, I want to have mass, the one mass, the other mass, and the acceleration of the system. So that's what I want to base my formula on. Now, it's also possible to have constants in there like g, the acceleration due to gravity, and all that. Okay? So, if you're taking the AP test, they're not going to want you to draw your free body diagram right on the picture. They're going to give you a dot that's going to represent the mass. So that's what we'll do here. So let's look at this. We're going to take mass m here and let that dot represent mass m. We know that we have a downward force of big mg, the mass, its mass times the acceleration due to gravity. We also know that there's an upward force Fn, and those two forces are going to be equal because we know that the mass is not accelerating that way. We know that there's going to be a tension force pulling it to the right from the string. And we also know there's going to be a frictional force pulling it back, and I'll denote that with little f. Now I want to point out, I didn't write it in this problem, but at this point we are not counting the mass of the pulley. Okay, so the pulley's not taking anything away from the system. That's going to come later when we talk about rotational inertia and all those kinds of things. But right now it's not mentioned, and the AP test or a physics test would say that there's, you know, the pulley's massless or something like that, so it doesn't really count. That's why I'm not counting it, if you're wondering. Now let's take the free body diagram that I just drew and write a few things about it that we know. Okay, so I'm looking at this diagram right here. Now if I look at the summation of all the forces in the y direction, that would be equal to the mass in the mass times the acceleration in the y direction. So here we go. In the y direction, the forces are Fn minus big mg, and I know that that's equal to 0 because there's no acceleration there. So I know that Fn is equal to big mg. Let's just kind of put that on the back burner. Now let's do the x direction. The summation of all the forces in the x direction is equal to ma. Now in this case, in the x direction, it's accelerating to the right, and I have that indicated by the fact that the tension is longer than the friction. Okay, so what I now know is T minus the frictional force is equal to m times whatever the acceleration is. Now remember, the acceleration is a variable I'm allowed to use. Now I also want to point out here that the frictional force is a percentage of force normal, and the percentage that it is mu sub k. Mu sub k is like the percentage times force normal. So I can replace this, I can put that in there for the frictional force, and that's what I'm going to do now. So T minus mu sub k Fn is equal to big Ma. But I also want to point out that force normal is actually big mg, so I can get rid of that variable too. So now I can write this. I can write T minus mu sub k mg, big mg, is equal to big Ma. And then I want you to put a little box around that equation. Okay. Pause the video, take a breath, make sure you understand that. All we did so far was we sort of just analyzed the state of that mass right there. Okay. Now, if you notice the equation I have two things in there that I can't use it. Well, I have two things that are supposedly unknown. I don't know the tension, right? I'm not sure what T is, and mu sub k is what I'm looking for. So I have to have another equation to be able to get rid of, say, the T, because I really want to keep the mu sub k. And what I do now is I say, all right, well, I'm going to switch now to this mass. So just like you'd see on the AP test, let that dot right there represent that mass. And then I know that I would have little mg down, and I know that I would have a tension up, and I want to point out that this tension and this tension would be the same tension since I'm not counting the mass of the pulley. Okay? So now for this one, I would say the summation of all the forces. I don't really have to indicate a direction because there's only one. It's only its only motion is going to be up or down. And that's equal to MA. So now I would have this. MG minus tension is equal to MA. And notice the M is little, just like it is in the picture, whereas over here the M was big, just to denote their different masses. Okay, now, what do I do with this? Well, I'm going to now take this equation, and I'm going to combine them. So let's do that now. We'll do that in this little box right here, okay? So the first equation is T minus mu sub K times big MG is equal to big M times A. Now I'm going to write this equation here underneath it, but I'm going to swap these terms around. So that's going to be negative T plus little mg is equal to little ma. Now, let me just say one more thing about this equation right there. You might be wondering why, if the mass is going down, I made mg positive and t negative. So what we did here, right, since it was accelerating down, I made downward the positive direction. Let me know in the comments if you want me to say more about that, okay? But that you can make positive any direction that you like. And I chose in that case, since mg was the winning force, to make the downward positive, which is why it's mg minus t and not the other way around. Now, let's take these two equations and combine them together. I'm going to add them up and the t's immediately go away. I've sped the video up here so that you can just see me solving this equation. This is just me running through a bunch of algebra. What I'm doing is I'm taking those two equations up top and I'm solving them simultaneously. And I'm using the process of elimination. So like I'm getting the t's to just add out because one's t is positive and the other t is negative. So now jump back into the video and let's finish this up. And now I'm going to multiply both sides by -1. And what I end up getting now is mu sub k, this is what I was looking for, and I'm going to distribute that to all those terms there. So that's going to make that positive little mg, that's this one, and then minus little ma, and minus big ma, and then the whole thing is over big M times g. And that's the formula that I wanted. Now, the next part of that question says basically, you know, like if I were to stack more mass on top of that, you know, if I were to put some more weight on there, like add 5 kilograms or something, would that change the coefficient of kinetic friction? Okay, so would that change that? Would that make that bigger or smaller? Now, I think the most knee-jerk reaction answer is to say, yeah, it sure would. But the answer is no. Okay, the coefficient of kinetic friction is a property that exists between two certain materials. Okay, it's complicated, but let's just look at the formula for it. Okay, so frictional force is equal to mu sub k times Fn. Now, I always tell everybody to think of mu sub k as a percentage. You know, it's a mod. This is a model, and the frictional force is related to force normal because the harder something's being pressed into the table, the more force normal is going to press back against it. So it's related to it, but it's a percentage of it, and that's a decent way to think about it. Now, if I think about the old function y equals mx, or y equals mx plus b, we're just talking about a line. So if this is like that. This is a linear relationship, where if this axis is little friction and this axis is force normal, you're going to get a line, and the slope of that line is going to be mu sub k. Now, nobody said that the frictional force won't go up as you tack more weight on. That's definitely true. But the slope of that line is going to remain constant. If force normal is some value, frictional force is going to be some value. If force normal increases, frictional force will increase. But mu sub k stays constant as long as the surfaces don't change. Now the next question says, I cut the strings while the masses are in motion. Draw free body diagrams for both masses at this moment. So like right after I cut the string, okay? Well, as far as, and let's do this one. So let's look at the mass M. Let's put a dot there like the AP test would. All right. What would the free body diagram look like? Well, there would still be mg down, and there would still be force normal up, and they would be the same. But now the thing is, there used to be a tension force pulling it forward, right? But now that would be gone. That wouldn't be there anymore. but there still would be a frictional force pulling it back, because this object, it would have been moving forward. It would have been accelerating forward because the T was pulling it forward. And it's not going to immediately just stop. It's going to take time to stop. So it's going to like skid to a stop. So while it's skidding to a stop, you'd have the frictional force. Excuse me. So that would be the free body diagram for it. Now, as far as the other mass goes, its tension force would disappear too. So this, let me just draw, as far as little m goes, dot representing that. The only force acting on that would be little mg, okay? Because the tension force that used to be up would now disappear because the string was cut. All right, here's the last question that we have on this problem, okay? So if you're taking AP Physics 1 or AP Physics C, you're going to be asked to do an experimental design question. And that basically means you got to tell the readers how you would design an experiment to find the quantity that you're looking for. So in this case, right, that's mu sub k. We were trying to figure out what mu sub k is for. Now, I like to develop the formulas for it first and go through that math. Some people would like to do this first, but here's what I think. We figured out what the formula is already. And what do we need to know? We need to know what the masses are. And we need to know what the acceleration is, because it said we have to get mu sub k in terms of the masses and the acceleration and any constants. And g is a constant. We don't really have to measure it. So basically, we got to be able to measure m. We have to be able to measure a. Okay, both m's and a. Now let's see. So first, what quantities need to be measured and what equipment is needed to measure each one? Remember, don't elaborate on your experiment just yet. Just answer that question to get that point. So what quantities have to be measured? Well, we have to measure the masses, okay? And to do that, we're going to need a scale or like a balance. You know what I mean? Like an arm balance, but some sort of scale to measure the mass. Okay, that's it. Then we're going to need to measure the acceleration. We need to do that. Now that, I would say the safe bet on that is not to say there's going to be you're not going to use some sort of acceleration meter to do it. What you're going to do is the old-fashioned way. You're going to basically do this. You're going to take this mass, which is going to fall. You're going to measure how far it falls, and you're going to measure the time to do it. So that means I'm going to need a meter stick or a ruler, whatever you want to call it, and a stopwatch. Okay? So there you go. We just answered that question. What do we got to measure, and what tools do we need to measure it? We have everything. Now we can sort of describe the procedure used and including necessary steps to reduce experimental uncertainty. Okay, so what are we going to do? All right, we're going to set this thing up. Right, we're going to set up this experiment exactly as it is, and we're going to release that mass, and the thing is going to accelerate forward. So that's the first thing that we do. Well, actually, no, I'm sorry, back up. The first thing we're going to do is we're going to measure the masses. So we got the masses. Okay, we measured those. Then we set this apparatus up and we let it go. And what we do is, once we let it go, we start the stopwatch. Once it gets to the floor, we stop the stopwatch, and now we know the time it took for this thing to fall. Now we also know the distance, because that's easy to measure. So we know the distance it took to fall because we can take a meter stick and just measure that distance. So then, all right, we got that. So there's the procedure. We measure the masses, we set the apparatus up, we release it from rest, we measure the time it takes to fall, and we measure the height that it fell from. That's the procedure, okay? Now, how are we going to do it? Well, we're going to do the procedure. Like, how are we going to do this to reduce uncertainty? We're going to do it, say, 4 times, multiple times. That would be a good way to say it. We're going to do it multiple times. And the reason for doing it multiple times is we can get all the different times that it falls. Now, the distance that we measure is going to be pretty accurate. We can get that pretty accurate. The error is going to come with the time. So if we do it, say, like 3 to 5 times, then we can take the average time, and that reduces some of the uncertainty in our time measurement. All right? Okay. So now we did that. Now, once you collect all that data, what do? Well, let's see. We know the masses because those are measured, all right? And then we know, put a little line here. So we know the masses, that's measured. Now we got to find the acceleration. And once we find the acceleration, we can just go back to use Newton's laws and we can figure everything out. To find the acceleration, we would say delta y is equal to 1/2 at squared plus v sub ot. We can use that old kinematics formula. This term goes away because we're dropping the block from rest. And then we would have measured delta y, and we would have measured t, so we can figure out what the acceleration is. Then we can just go straight back to the masses, use Newton's laws, and we can calculate what that missing force must have been.